the discharge measured at a certain time here, that is this value here measured, it is affected by rainfall that fell during the first pulse. It is also affected by the second pulse, and it is also affected by the third pulse. So now what happens is, using the unit hydrograph, we generate a unit hydrograph for the first pulse, we generate for the second pulse, we generate for the third pulse, and the value measured at this point will therefore be the effect of the first pulse plus the effect of the second pulse at that point and effect of the third pulse at that point. So what this means, the effect from the first pulse will be felt, let's say, two steps earlier than the effect of the third pulse, for example. So that is what this part talks about. This part is talking about. Sorry, not that part, but this is what this part is talking about. So you have to break the effect into M parts. M parts, you know the number of pulses. And if you do that, therefore, Q of N can be calculated as an integral of the inflow into the system times the response function U of N dt minus tau d tau. And then if you break it into M parts, if you break the 0 to N dt into N parts, there's something that there's a mistake I did here. This effect can only be measured within the period of the pulses, because we have two equations. So this one I will explain it a little bit later, but now this explanation I was talking about is the response that is measured during the time of the rainfall. But even for both, that is what happens. For both cases, that is what happens. So you notice the Q of the N, this NDT is broken into M parts, until we get to the MDT, until we get to the end of the rainfall. That is during the rainfall period. If you apply, therefore, the limits that tau is equals to M minus 1 dt, as L is equals to N dt minus that, and the limit tau is equals to M dt becomes N minus M dt. If you apply those limits, then the output, or the mth integral in the previous equation becomes the mth integral in the previous equation. The mth integral in the previous equation becomes P of M of the pulse unit response function N minus M plus 1 dt. And this particular equation, you will notice later that it is kind of the basis. It is kind of the basis of the convolution equation, discrete convolution equation for unit hydrographs. And if you make the substitutions in the equation 16, whereby you are substituting the mth integrals appropriately, whereby, for example, P1 when we are talking about P1, we are saying 1 M is equals to 1, P2 M is equals to 2, P3 you will have, if M is equals to 3, then you are going to have a P3H N minus 2 dt and so forth and so on. So if you substitute this general equation into the previous equation, then you end up with this expression for Qn. This is only when rainfall during the rainfall period and also even after the rainfall has elapsed. And generally, the equation 18 is the convolution equation with input PM in pulses and Qn as sample data function of time. Let us also look then at, so we have looked at the linear. We were looking at the linear system in discrete time. So here, in equation 18, we are seeing the relationship between discharge and rainfall in discrete time. A relation between discharge and rainfall in discrete time. So let us look at the discrete pulse response function. And this discrete pulse response function is the unit, the pulse response function is response given a unit pulse, response given a unit pulse. And now we can write the response function in terms of the time domain that we have established in the convolution equation, that is n minus m plus 1, n minus m plus 1. And why n minus m plus 1? Because that is the response, that is the response time, that is the response time of Qn, that is the response time of Q, of n, of time of Q measured at time n. So the U of n minus m plus 1 can be given generally as h of n minus m plus 1 dt. And this equation comes from the formula 12 of the pulse response function. From the formula, if you go to the formula 12, you will be able to see how this equation has been derived at. And in a similar manner, then you can write u of n. You can write u of n minus 1. You can write, until you get to u of n minus m. M is the last rainfall pulse plus 1. And if you now substitute these values in equation 18, in the discrete time version of the convolution integral, then you will get, and you simplify, you're going to get this expression, Q of n is equals to summation m is equals to 1 to m, P of m un minus m plus 1. And I said, when we were giving the examples, and I think it was in, I don't know which diagram it was. Let me check whether it is still there. Yes, during this diagram, the discharge, the response, which is a discharge, is an effect of all the pulses during the rainfall and even after the rainfall. And that is what this part says, that this equation 20 is valid even when n, the time n, when we have measured rainfall, is greater than the time when the last rainfall was measured. And this is a very critical equation, and you will see. Now, if n is less than m, and what do we mean by n is less than m? The n is less than capital M. And let me try to explain a little bit here. Capital M ends at that point. Capital M ends at that point. So N, when the discharge is measured, can be equal or less than M, or it can be equal or it can be greater than M. If it is equal or less than M, it is, you have measured it within this time here, for example. But if N is greater than capital M, you have measured the discharge after the rainfall has ended. Yeah, so for N is less than M, the Qn is basically the convolution equation. For and if you combine both equations 20 and 21, if you combine, because now here Qn for rainfall is greater than M, that will be Qn M is equals to 1 is equals to N, and N is greater than M. If you combine both equations, you get the discrete convolution equation. Discrete convolution equation Qn is equals to M is equals to 1, N is equal or less than M, PM UN minus M plus 1. So what this means, if you have 3 rainfall pulses, if you measure the rainfall within the first pulse, then you are only going probably to have calculate Qn as a function of 1 pulse. If n is 2, you are going to calculate discharge as a function of 2 pulses. If n is 3, you are going to calculate Qn as a function of 3 pulses. If it is 4, you are going to calculate Qn as a function of 3 pulses. You cannot calculate the discharge with more than the maximum number of rainfall pulses. So that is what it means, and you will see it a little bit clearly from an example. So I want us to take note of this equation. You can consider this equation separately, but most importantly, I want us to take note of this equation. So what usually happens then, using this discrete convolution equation, we can be able to calculate un of m, u of n minus m plus 1, which is the unit hydrograph. Or if we are given a unit hydrograph and we are given rainfall, we can be able to calculate Qn. So that is the principle. If you are given a unit hydrograph of a catchment, you have measured rainfall in that catchment, you can calculate Qn. But first, how do you get the UN? You have to analyze the data, maybe of very, very many observations, and first, using rainfall and discharge relationships, calculate your UN. For example, simply UN is equals to Qn divided by PM. And Qn is, you multiply rainfall by the unit hydrograph, basically, in simple terms. So the notation n is less than m as the upper limit of the summation shows that terms are summed. I think I explained that already. For n is less than m, but not for n is greater than m. Terms, you can only calculate Qn using 3 terms. For example, if you using a maximum of 3 terms, if m, the number of pulses is 3, for example. And I'm giving an example of 3, and then we have 3 here. So here we have an example, a very nice one, and I like it. So for example, Q1, and I mentioned it, will be equal to P1 U minus 1 plus 1, P1 U1. So you only calculate it using one expression. Q of 2, use 2 expressions. Q of 3, using 3 expressions. What about for n is now greater than 3? What about when n is greater than 3? Qn will be, the general expression will be P1 times unit of hydrograph expression for the nth time plus P2 n minus 1 plus P3 un minus 2. And for you to be able to derive this, I want you to apply this, let me delete this one. For you to calculate that, you apply this expression. So for example, in this case, let us calculate Q of 4, Q of 4. Q of 4 will be summation, m is equals to 1 to n. And if we, our n is 4, our total n is 4, then we are going to calculate P of m, m is equals to 1 to n, un minus m plus 1. So Pm, the first expression will be P of 1, U of 4 minus 1 4 minus 1 plus 1, that will be U of 4, P1 U4. Then if m is equals to 2, if m is equals to 2, P of 2 un minus 2, 4 minus 2 is 2 plus 1, 3. And then if m is equals to 3, and 3 is the maximum, Q of 4 will be Pm, plus. You remember summation, you have to add P of 3, n is 4 minus 3, that is 1 plus 1 of 2. So now un, you have un, P1, U of 4, P2, U of 3, and P3, U of 2, I think. I think I'm not writing down, so I think that it should be that way. So generally, for this example with m is equals to 3, you can only have P1, P2, P3, and then U4, U3, U2, U4, U3, U2. And you can calculate, for example, can someone write for me Q of n? Someone write in the shared notes. U of, or in the public chat, Q of 5. Q of 5 using this general expression. Someone, who am I going to ask? A volunteer. I want a volunteer because I wonder if everyone is following. Someone, today I start from the bottom. Tanya Adhiambo, can you try to write the Q of 5? Or let me ask, Q of 5, what will be U of n? What will be the value of n if we are doing Q of 5? What will be the value of n? Tanya Adhiambo, what will be the value of 5 of n? Suleiman Kondo? If we are talking about Q of 5, then that means n is 5. So if n is 5, n here will be 5, n minus 1 will be 4, n minus 2 will be 3. Okay, so because I've given an example of that, we are writing Q of 6. Charlene Jerry, what will be the n in the first term? Or anyone else who is attentive, you can tell me what that value is going to be. N will be 6, and then n minus 1 will be equal to? And that is correct. And then n minus 2, n minus, it is n minus what? N minus 2 will be equal to 4. So can someone write for us an expression, because now we have gotten it. Can someone write for us Q of 8, the complete expression, Q of 8? Can someone write for us the complete expression for Q of 8? And you can write P brackets of 1, U brackets of, whatever. Someone? You can write in the shared notes, or you can write in the wherever. Someone write for us Q of 8, another one Q of 9. And your two, I want us to finish with that exercise. Oh, they are written here. Oh, the answers are written here, sorry. let us, but generally I think you can see what we are talking about. Generally you can see what we are talking about. So at the end of the day, you find that at the end of it, only one pulse will be contributing to discharge, and that is the last pulse, which is P of 3. Okay, so so Q and PM we talked earlier are expressed in the thank you very much. Thank you very much, Brian Obumba. Which part do you need explanation for, Obure, before we take a roll call? And before we come to before no, you of eight, Tevin Brandon, haitakuwa na tatu. Remember, you have to use the equation. Let me check the particular equation. The equation 21 and 22. You have to use the equation 21 and 22, and I'll come to show how we eliminate those terms. And Obure is asking for an explanation. So before I come to the explanation, let me see if we can finish that part. Before, because I had talked about the discharge Q and P of M, the discharge Q and rainfall being in different dimension, and the U as dimensions that are the ratio of the dimensions of Qn and Pm. So that we can make the equation 22 consistent. Yeah, so so that is it. So let us go to, I want to see Q of 8 is P. So let us see, let us try to apply the discrete convolution equation for P, starting from Q of 7. And I need to take a pen even myself so that we can do it with you. And this particular equation, and even the way we are doing, is the basis, is critical, is very critical when we are doing this unit hydrograph part. So we better understand it. So give me a minute, I cut a pen. I need to write it first down. The equation is Q of n is equals to summation n m is equals to 1 pm un minus m plus 1. So this is equation for n is greater than m. N is greater than m. So Qn is equals to m is equals to 1 to m pm un minus m plus 1. Then we come to so here we have Brian Obumba for Q8. We have explanation for that, please. Then we have Tevin Brandon, and then we have Mwiga Mutero. I want us to take a break because it's already 8:05. And then when we come back, I will show you why we are eliminating the first two terms in the PU of 8. Because all we have to do is write this general expression into actual terms. And then Obure Zachary, if you can speak, you can tell me which part you want explanation, so that when we come back, we are going to concentrate with that part. Obure Zachary, which part do you want explanation for? Okay. So when we can, let us take a break of 10 minutes. Remember, I'm now taking a roll call. The poll, the yes or no. Then when we come back, we are going to look at that particular part. Before we now continue to the part 2, which is the actual application. At a poll, yes or no. So Brian Bisonga, Debbie Zephania, John Akinyi, Melvin Anthony, Nyaga Nixon, Peter Jaroge. John Akinyi, Melvin Anthony, Nyaga Nixon Mutwiri, and Victor Kangor. Oh, John, you're present. Present. Hunter Macharia is in attendance with Bronson Kibunyi. Okay. Yeah, so let us come back at 8:20, and then I'm going to solve, P of 8 using examples, P of 7 and 8 using examples. Okay, so first we start with the explanation. What was his name? Obure asked, and he's offline. He asked, we explain about what we have just talked about. So I said the convolution equation, discrete convolution equation for a linear system is the core. It is the core of unit hydrograph analysis. Now, we have been able to go through the steps of first writing the discrete, the response functions, the unit response functions in continuous time. We have been able to write the discrete linear response functions, and then from that we got the convolution equation partly. And then finally, we came and developed the discrete convolution equation. Discrete convolution equation, and if I can delete that. And this is the general plus 1 we need to be able to determine that. Why am I forgetting this? How to get the 6 non-zero terms. I just solved it. Where is the diagram being referred to? The diagram is in the next page. The diagram is in the next page. The diagram is in this page. The diagram is this one on this page. I need to remember something. I'm forgetting how. I need to be able to expand this. Allow me to do this, and then I'm going to post in on the WhatsApp group, and then I'll explain. I'm just forgetting. I don't know why, and I really used to do it like clockwork. Anyway, but that is the general convolution equation in discrete time, and I will show you how to expand this equation so that you can come up with your actual terms. So allow me to come back with that explanation. So basically, and what I'm talking about, we need to be able to know these this equation. That is equation 20, 21, 22. 22 is the general equation. Equation 20, you use it when you're calculating the response when the rainfall is ongoing, and then 21 when the rainfall has stopped. So in summary, this is what we are talking about. So from the pulse 1, you have a unit hydrograph. From the pulse 2, you have its unit hydrograph. From the pulse 3, you have the unit hydrograph. Then unit response function, the impulse function. So the total response for this particular time is only this value of U1. In the second, it will be a summation of this response plus that response. And then in P1, U3, you add the 3, you continue adding the 3 until the time now you end up with the maximum 3, 2, and 1. And I will expand the equation and then get back. I can get back through WhatsApp, or I can explain it during the next class. So this is about this unit response function. Apart from that question by Obure Zachary, apart from that question from Obure Zachary, anyone else with another question? Because I want to check, we are supposed to now go to the unit hydrograph itself, and start applying the convolution equation. We need to go that. In which case I need to upload the part 2 of these notes. Bill Clinton. I was talking to myself. So Muiga says, please avail examples with actual figures. Of course, yes. Now, when we come now to the actual unit hydrograph, we are going to be applying it now in actual situations. Then Bill Clinton, he's following keenly. That is okay. So the unit hydrograph is the unit pulse response function of a linear hydrologic system. And it has a definition that it is the direct runoff is the direct runoff hydrograph resulting from 1 centimeter in SI units of excess rainfall generated uniformly over the drainage area at a constant rate for an effective duration. So notice a number of characteristics of the unit hydrograph. It's direct runoff hydrograph. It results from 1 centimeter of rainfall, of excess rainfall, over a complete drainage area at a constant rate. And the constant rate, that is what I wanted to show. So during the period of generating the unit hydrograph, the rainfall intensity is constant. Before we continue, I want to ask a question. In engineering hydrology 1, we did we know how to calculate excess rainfall. Anyone who can tell me methods of calculating excess rainfall, because in the examples that we will use, you will definitely have to calculate excess rainfall. And we have to do a recap. How do we calculate excess rainfall? I want us to do a recap. I want us to think about that, and we can answer in the questions. So there are, you can answer as we continue. You can try to write answers as we continue. It is a simple linear model, and it can be used to generate a hydrograph resulting from any amount of excess rainfall. And we have a number of assumptions. Number one, and before I go to the assumptions, I'm requesting a definition of excess rainfall and some methods that we can use to calculate excess rainfall. So the excess rainfall, one has a constant intensity and with an effective duration. It is uniformly distributed throughout the drainage area. The base time of the direct runoff hydrograph resulting from the excess rainfall of a given duration is constant. What is the base time? If you have a hydrograph, the base graph, the base time is the time between, the time. And if you have calculated and determined and do, and if you have calculated the base flow and determined that your base flow goes like this, then your base time will be the time from the start of the, storm hydrograph to the end of the storm hydrograph. That is the base time, the period between the start and the end of the direct runoff. Then the ordinates of all direct runoff hydrographs of a common base time are directly proportional to the amount of direct runoff represented by each hydrograph. And then for a given watershed, the hydrograph resulting from a given excess rainfall reflects the changing characteristics of the watershed. So if you remember how we did excess rainfall, and you will have to know this bit of calculating excess rainfall for you to be able to apply and use this unit hydrograph. And in the problems that we will solve even in exams, you may be even required to do the excess rainfall. So we better start answering this from our engineering hydrology 1. What is the significance of these assumptions? Because one, if the fact that we're even assuming means that in reality, they may not be achievable, but they have their significance. And, we can, normally when we assume in science, we usually make educated assumptions so that we can be able to defend our assumptions. So normally in science, when we use assumptions, we select our data so that our assumptions are almost met. So for the assumption 1, when you are selecting data for unit hydrograph, you select storms that occur during a very short duration, because such end of storms will produce intense and nearly constant excess rainfall rate, which will produce a well-defined single peak. So short duration is correlated with nearly constant excess rainfall. Then 2, the unit hydrograph may be inapplicable when the drainage area is too large. Because if the area is large, it may be difficult to achieve a uniform distribution of rainfall. So it is best to consider relatively small drainage areas. Then the third assumption about the time of the direct runoff is generally uncertain, but depends on the base method of base flow separation. So when you are selecting the base time, you have to know at the back of your head which component of direct runoff are you talking about. In literature, direct runoff is usually considered sometimes to comprise only of that water overland flow only, but sometimes we have what we call subsurface runoff, that is some parallel ground, subsurface flow just below the ground, which is considered to occur just below the ground surface. It's like a short circuit. Water infiltrates but does not percolate, but flows parallel to the ground surface and joins overland flow at rivers, natural drainage channels. And then finally, assumption number 4, the principles of superposition and proportionality that we talked about that apply in response functions, solution of response functions, whereby a sum, if you add two solutions of the response function, then the sum is also a solution. And then proportionality, the proportionality which assumes that a multiplier or a multiplier of a solution is also a solution. So we assume those two so that the ordinates of Qn and of DRH may be computed using the discrete convolution equation. And in this assumption, at the end of the day, we say the hydrologic data are usually not truly linear. And when we apply the equation 22, then the resulting hydrograph is usually an approximation. And that is why this knowledge, based on this knowledge, because this hydrograph is used when we are doing maybe rainfall runoff modeling, when we calculate these hydrographs, because of this kind of background information and assumptions we have made, we know that the resulting answer is not accurate. It's not, a completely true representation, but an approximation. And because of that, we usually use observed data to try and calibrate our models. And then finally, on the assumption number 5, the unit hydrograph is considered unique for a given watershed and invariable with respect to time. So the unit hydrograph for Athi River, for example, of course, the river is too big, so you may have to break it into subcatchments so that you can have small subcatchments. But imagine a small subcatchment of the Athi River. It won't be unique when you compare it to a unit hydrograph of another catchment and what have you. And it does not vary with time. It does not vary with respect to time. And this assumption can be challenged because we know, for example, excess rainfall can be affected partly due to characteristics of the catchment. And imagine if we have development, like development of an urban area or deforestation in a certain subcatchment, we can fundamentally change the surface onto which the water flows. And because of that, the unit hydrograph may end up changing. But then what this means, if the issue of time invariance, then you can apply the unit hydrograph over a very short duration of time so that that assumption applies. Because during a very short period of time, then changes in the physical characteristics of a catchment may be also very small too for the assumption to apply. This principle of time invariance, the principle of superposition and proportionality are fundamental to the unit hydrograph model. Because of these, unit hydrographs becomes inapplicable, or it is not advisable to use them when we have changes in channel conditions, when you have changes in watersheds that have storage, for example, which have many reservoirs, or when you cannot be able to measure the river discharge correctly because we have floods and what have you. Now, I have given a figure. Somewhere. That is figure. It should be figure 1, where I have compared linear system concepts with corresponding unit hydrograph concepts in hydrology. And the step response function is usually called the S hydrograph. The impulse response function is called the instantaneous unit hydrograph, which is the hypothetical response to a unit depth of excess rainfall deposited instantaneously on the watershed. So we have two here, the Hess hydrograph and the instantaneous unit hydrograph. So you can look later. You can look later at that image, and then you'll see the correlation of the two. And all along, I've been explaining anyway the unit hydrograph derivation using examples of actual applications. So how do we derive the unit hydrograph? By applying the convolution equation. Convolution equation. So the discrete convolution equation. Now the reverse of this, which is the reverse, is when we are determining the unit hydrograph U of n, is called deconvolution. It's called the deconvolution, and we derive it by solving a set of questions, a set of equations that are developed using discharge and rainfall data that we had already seen before, like what we did, whatever I'm supposed to show you a little bit later. And normally the set of equations, from the set of equations, you can develop a matrix which has more equations than the unknowns. You make a set of so many simultaneous equations with more equations than the unknowns. So normally the matrix is overdetermined. And the set of discrete equations is basically the table 2 is basically the table 2. I don't know why I'm calling it table 2. It should be the table 1 and then table. I have changed the table 2 and table 1. I'm telling you. So this is the set of the discrete, you can call it matrix or the set of equations. They are usually excess and excess with I think 1 or something. So it is usually overdetermined. So it is, you can solve it directly. And yeah, this is the comparison. A linear system, the watershed, and I don't know whether I explained. Yes, I did explain the concepts. Then unit pulse response function, excess rainfall, unit step function, and then the ice hydrograph. This is like a mass curve of a hydrograph, and then unit impulse. Then this is instantaneous unit hydrograph. So we have severally tried to explain these similarities. So we have an example. Find the half-hour unit hydrograph using the excess rainfall hydrograph and direct runoff hydrograph given in the table below. The excess rainfall hydrograph and the direct runoff in table 3 have m is equals to 3 and n is equals to 11 parcels, respectively. So I want us to go through this example. The rainfall is in inches, direct runoff is in CFS. But remember, I still need to show you how to expand the equation so that you can have the correct number of equations. Now, I have asked a question. Because I think after this we have others. We have other methods of linear programming. If we have other hydrographs, unit types of hydrographs, which we shall see. But today I wanted us to reach to the unit hydrograph and finish with the derivation. And I do not want us to proceed. I don't want us to proceed without me explaining how you expand that equation. So I will want to explain that one first. But I asked a question, and Amujajibu, I asked, what is excess rainfall? Because it is critical, and that is one. Then two, how do we calculate it? We have a few minutes, like 6 before the end of the class. New volume took. You people, for us to continue, I want us to answer that part. So let me see whether I'm going to surface water. Let me see whether I have that information. Let me see if we have it somewhere. Yeah, so I talked about the excess rainfall and direct runoff. And my question is, these are notes from Engineering Hydrology 1A. I did not teach you, and it is very important that I know that, because you will have in the questions that you will solve even in the exam, you'll have to apply some of these principles of excess rainfall and direct runoff. And what I can do is wow, I don't know. Not unless you tell me, I will not know whether we can continue or you can't. If we remember these concepts of deriving the excess rainfall, its definitions, and the various aspects that are involved. Someone volunteer and give me an answer. And please encourage the teacher so that I know we are together. I know we are talking. Of course, you're asking questions, and I'm very happy. But encourage the teacher. Yes, it is the rainfall that is available for surface runoff. That is correct. That is correct. Very correct, Bill Clinton. Thank you. And do we know how to calculate it? A number of methods on how to calculate it. Yes, excess rainfall is Caroline Kavutha's total rainfall minus sum of all losses. Do we remember the methods? So minus sum of all the losses. So some of the methods of calculating surface runoff. And okay, briefly, let me just take you through. But now I can see we get the concept, and that is okay. Rational method, no. Rational method is a design method for urban systems. It is not. It is not. And that one I want to repeat. It is not used in calculation of surface excess rainfall. And phi index method, that is correct. Then we have, of course, this is whatever we have here is the phi index method. That is the, we have the runoff coefficient method, and then we have the phi index method. Those are the two main methods. And then we have another method. We have a third one, this SES method. We have another one when we use abstraction, using infiltration equations. And that is when, sorry, we have two categories of methods. One, when stream flow data is available, then you can use runoff coefficients and phi index. When stream flow data is not available, you can use, one method is calculating abstractions using infiltration equations. And secondly, you can use the SCS method for abstractions, where you use the curve numbers. I don't know whether you came about the curve number method. But that one it's not a curve number method, but it is a SCS method of abstractions, and so forth. Now, in the case when you have data, stream flow data, in the case when you have stream flow data, like in this case, first you have to estimate the base flow from the discharge, and then subtract the base flow from the discharge, so that you can be able to calculate the direct runoff hydrograph. And then after that, you can apply the method. So number one, and because the data that we will be using in the examples, I can we can use a discharge hydrograph that we have been given, which first you have to remove. You have to separate the base flow so that you remain with direct runoff hydrograph only, and then you apply our unit hydrograph method. So that is what I want to share. Of course, but remember, rational method is a method, and I don't know whether I have something somewhere. It is only used in design of, it's mostly used in urban hydrology, and I don't know. Yeah. 493. Let me just check in the textbook here. And I will define to you the rational method. Rational method is a method that is used to calculate the maximum peak. The rational method is only used to calculate the maximum peak. The amount of intensity. Yeah, so it is the rational method is only used to calculate the peak discharge Q, and in excess rainfall we want to calculate all discharges and not only the peak discharge. But I know many many of us are not able to differentiate those things, but it is very important. To know that. Now, today, yesterday we were having a discussion at night. I sometimes work late, so when you see me even online, that means my working time is still on. So sometimes when I'm working at night, I can solve some of the work problems. We said that we can extend this morning class up to 10, but today my schedule is already packed. Today my schedule is a little bit packed. So from next week, we will now start increasing the time so that we can be able to cover more ground. The derivation of the unit hydrograph takes time, and I think the rest of the parts are not that consuming. Well, maybe a little bit. This is this is an advanced level of hydrology, but the derivation of the unit hydrograph, I think, is the most complex of all. So any question? So I want us to go back to our notes, try to remember the rainfall, the runoff coefficient method of calculating excess rainfall, base flow separation methods, and then the phi index method. If you learned the curve number method or the SES method, you can look at it. If you learned the method where you use infiltration equations, you can also look at it. But make sure at least you familiarize yourself with one of these methods and also the base flow separation methods. Any question? And, I'm hoping that we're going to respond, because we are not living if you don't respond. I want communication. I want to talk with us. I want us to communicate. Any question? Nganga Amos, any question? And then in the meantime, I take the poll. In the meantime, I take a poll so that I know who is in and who is not in. And kindly, someone, okay, that was who? Nganga Amos, no question. Okay, Tevin Brandon. Volunteers, you can say something so that I know we are together. So people, Bill Clinton, as you are not in, Alicia Higgins. We have Tevin Brandon, no question. So I want to ask some people who have not responded to the poll. We have Alicia Higgins, Hunter Macharia, John Akinyi, Peter Joroge, Totona Brian. So probably I should write those names. I suggest to use example. Chebi Zephania, which example do you, if you could talk, Chebi, if you could speak, I don't know, which example are you talking about? In unit hydrograph application or base flow separation? Because when it comes to the unit hydrograph application, we are going to do so many examples. We have so many examples in the tutorials. Yes. Morning. Oh. So I don't know what is happening, but I responded to the poll. Okay, Chebi. So Chebi, Chebi, I don't know. You are talking about the unit hydrograph. That one we are going to do so many examples, so don't worry about it. Antonio Ondima, you want me to send my notes for determining excess rainfall? Aha. All right. Let me see. Let me see how I can extract that part of the notes and send them to you, because they also have examples on how to use them. They have examples on how to use them. So people, it's now 9 o'clock. From next Wednesday, we will increase the hour. We increase up to 10, and that can help us. So thank you. Before then, I will also send a detailed description on how to expand the discrete convolution equation. And if mukiona delays, munikumbushe. Don't shy away. And class, this is not what we agreed on. You are not responding. You are not, you are passive. I want you to be active. When we are waking up very early, it is good to have a feeling that we are in this together. Eh? Not that I've woken up and alafu naona ni kama tu pia sisi wote tumelala. I'll get sleepy and discouraged. So let us encourage each other. Otherwise, thank you for coming. Before you leave, let me save the attendance. And class, communicate to the rest of the class to try and join the classes, because if they do not attend 80% of my classes, they're not going to take the exams. As Anta Macharia is in attendance with Bronson Kibunyi. Those people who are attending with colleagues on their phone, together, they can always let me know so that I do not consider them absent. So good day all.